Welcome back. This is the day the Lord has made. Let us rejoice, be glad in it. In this video, I'm going to talk about isomers for organic chemistry. This will be the last video that I talk about organic chemistry stuff. So isomers, this is talking about how chemicals can have the same formula, but be arranged a little bit differently structurally. So the big idea is you got these big branching hydrocarbon chains. The carbons could be like, if you had 6 carbons, you could have a branch that's just 6 carbons long. Or you could take one of those carbons from the branch and make the longest chain 5 and add that one carbon somewhere else. And now you have a branch on there. It's still the same chemical formula, C6H14, but now it's going to be a little bit different. So that's the big idea. So for example, up here, butane would be C4H10. We have 4 carbons, 10 hydrogens. We could rearrange this and take one of the carbons and branch it off instead. So again, the chemical formula is still C4H10. So we have 4 carbons in this molecule, but now we have a branch. These are the same chemical formula, and you won't be able to know that by just looking at the formula. Isobutane or 2-methylpropane has the same chemical formula as butane. So when we did stoichiometry and I just wrote the chemical formula, like C6H12O6, that doesn't tell you how it's actually built. It might be a different molecule, but with the same formula. Those things are isomers of each other. So again, some other examples in real life would be things like some carbohydrate ones, like glucose and fructose. They're the same formula. They both have the same chemical formula, but they're different. Now, we should mention that our body is very particular to the actual arrangement of molecules, all right? Meaning like our body has an enzyme specifically for glucose, and now our body has enzymes specifically for fructose, and they're different. And so our body cares. Like your tongue is like a generalist. When you eat something, like if it tastes like sugar, if it feels like sugar, your tongue says it's sugar, all right? Because another example would be like fake sugar. So the difference between fake sugar and real sugar comes down to just they're isomers of each other. They're the same chemical formula, but they just change where maybe an OH is attached. So again, looking down here, glucose and fructose, all that's happened is we've changed where this double bond is with the carbon. So we just made a little addition, a little change right there. And so that little change there, it's the same chemical formula, but it looks different. It doesn't fit the same. So real sugar, fake sugar, what they might do is they might just change which side the OH is on. And so here we can say, oh, let's take this OH on the glucose and we'll put it on the other side. So on the 1, 2, 3, on the 3rd carbon, counting from the bottom up, rather than having the OH on the right side for glucose, for galactose, we'll just put it on the left side. And so the difference between fake sugar and real sugar is we just move an OH around, or we just change something about the molecule. And so the tongue says, yeah, this thing looks like sugar. It feels like sugar. It's about sugar. But the enzymes in our body are very specific, and they will not fit onto that molecule. And so when you eat fake sugar, your enzymes don't process it. Again, another good example of real life isomers would be like baseball gloves in your hands. Your hands are isomers of each other, all right? So both of my hands have the same chemical formula. I have 4 fingers and a thumb. They have the same formula, but they're not the same. They're different. They don't fit a glove the same way. Think about an enzyme being like the glove. I can't put my right hand into a glove that's supposed to be for my left hand. It won't fit. And so the same thing is with like chemicals. If you just change how it's structurally arranged, you give it a new personality. You give it a new, it's a new flavor. It's the same chemical formula, but it's a new thing. All right, those are isomers. So there's different types of isomers. In this class, we're going to focus on pretty much just structural isomers. All right, so we're just basically getting into it a little bit. Structural isomers are all about how it's arranged. So we could put a fluorine, it's kind of hard to see in this little picture here. There's a fluorine on the middle carbon, or the fluorine could be on the outside carbon. So this is 2-fluoropropane, this is 1-fluoropropane. Those are structural isomers where we just take one of the attachments and move it around. Spatial isomer, that's where we actually just change the orientation in 3-dimensional space. All right, so that's like my hands here. My hands are spatial isomers of one another because they're a mirror image of each other, which again, a mirror imager, we call those things enantiomers. So they're a mirror image, but they're not superimposable. They're different. So mirror image, but not the same. So again, on the example on the right side, this carbon has a fluorine, chloramine, and bromine, but they're in different orders as they arrange themselves. So they're a mirror image, which means that this carbon with these guys would not superimpose on that. They're different, all right? This is like my right hand and my left hand. They're a mirror image, but not the same. And so again, if you're a mirror image, you have different properties, all right? And so this is also important too. And so there's different ways to talk about this. Like for this kind of one, we'd use an R or an S notation. Is it a right spin or a left spin? Again, we're not going to go there in this class, but it's good to know that, hey, it's even more complicated. It matters, not only does it matter where you put the fluorine onto the carbon, it matters what position it's on the carbon, and you get a new structure, you get a new chemical. One thing that's we hear about a lot are things like trans fats, all right? Trans fat versus cis fat, those are just talking about isomers as far as location on a double bond, all right? Cis means same side. Trans means opposite sides. So if you have like a double bond, how the branch continues on, how the chain continues on, it matters. So on a cis fat, what happens is the double bond branches back in the same direction it came from. So it's going to curve back where it came from originally, and you're going to have the hydrogens on the same side and the main chain on the same side. A trans fat is when there's actually an opposite side. So a trans fat, you have the hydrogens that have been switched sides. So a trans fat versus cis fat, the only difference is, are the hydrogens on the same side or are they on opposite sides of the double bond? That's the difference between a cis fat and a trans fat. All right, so naturally occurring fats tend to be cis fats. Trans fats are artificially produced. But so in this class here, we're not going to talk too much about those things, but we are going to worry about like structural isomers. So some of your questions ask you, how many ways could you make this? I'm not asking about spatial enantiomers. I'll be talking about structural isomers for those questions. So you might have a question like, well, how many isomers could you make with this chemical formula here? And we're going to ignore the spatial, just the structural. So when you draw it out, if it's a new structure and it has a new name, it's an isomer, but it has to have the same chemical formula. If it's the same name, it's not a new molecule, all right? So here's some examples that would be isomers. We could put the fluorine on the first carbon. We could put the fluorine on the second carbon. So 1-fluorobutane, 2-fluorobutane, those are isomers of each other. We could also take this 4 carbons and make it so that instead of being 4 long, we'll make it 3 long and put an attachment on there with another carbon chain. So we have still 4 carbons because we got 1 methyl propane. That means we have 1 carbon as a branch, 3 carbons the main chain. That makes 4 carbons. So we have 4 carbons and we have the fluorine attached. This is something new. So here's another one. This does not count. Why? So why would not count? Because if you count it out left to right, this is not on the third. There is no 3-fluorobutane because you would name it 2-fluorobutane. You can't get to the third by making it have the smallest number possible. So this is 2-fluorobutane. This is 2-fluorobutane. So we don't have a 3-fluorobutane. So something else to mention too when it comes to this is double bonds and triple bonds. You need to have the same number of hydrogens too. So if some molecule has a double bond and another molecule doesn't, for hydrocarbons, they're probably not isomers of each other. All right, Godspeed.